The Kuiper Belt isn't the peaceful graveyard we thought. It's an active threat zone containing horrors we're only now beginning to detect. A frozen wasteland hiding threats that dwarf anything Hollywood has imagined. And here is a question. If you could teleport anywhere in the universe, where would you explore first? Comment down below. I will pin the most creative answer. Now let's begin. Recent observations from NASA's New Horizons spacecraft have detected something unexpected as it speeds through the outer edges of the Kuiper Belt. The spacecraft's Student Dust Counter instrument, designed to measure tiny particles of ice and rock, has been picking up higher levels of dust than scientists predicted, and we're not talking about a small difference. The readings defy the models that suggested the density of Kuiper Belt objects and their dusty remnants should decline at certain distances. Instead, the dust levels remain stubbornly high, hinting at one of two possibilities. Either the main Kuiper Belt extends billions of miles farther than we thought, or there exists a second, entirely separate belt beyond the one we already know. Think about what that means for a moment. We've spent decades mapping what we believed to be the outer boundary of our solar system's planetary construction zone, only to discover that the blueprints might be incomplete. Imagine building a house and thinking you've explored every room, only to find a hidden doorway leading to an entire wing you never knew existed. That's essentially what's happening here, except the stakes are cosmically higher. This isn't just about satisfying curiosity, it's about understanding the architecture of our cosmic neighborhood and the forces that shaped it over 4.6 billion years. Now you might wonder why a bunch of frozen rocks billions of miles away should matter to us here on Earth. Fair question, but the Kuiper Belt isn't just a cosmic junkyard. It's a time capsule, a pristine archive of the raw materials that built our solar system. Every planet, every moon, every asteroid, and yes, every atom in your body came from the same swirling disk of gas and dust that collapsed under gravity's patient pull all those billions of years ago. The Kuiper Belt objects, unlike the planets, never underwent the intense heating, collisions, and transformations that erased much of the inner solar system's early history. Out there, in that frozen darkness, the original ingredients remain largely unchanged, waiting to tell their story. And speaking of stories, let's talk about one of the most remarkable objects New Horizons encountered during its journey through the Kuiper Belt. On January 1st, 2019, the spacecraft flew past a small, strange world officially designated 486958 Arrokoth, though it was initially nicknamed Ultima Thule. Arrokoth is a contact binary, meaning it's actually two separate lobes that gently merged together eons ago, creating a shape reminiscent of a cosmic snowman. When the images came back, and remember, it takes hours for radio signals to travel from the Kuiper Belt to Earth, scientists were stunned by what they saw. Arrokoth measures roughly 22 miles along its longest axis, and its surface is remarkably smooth, bearing very few impact craters. This tells us something profound. Arrokoth formed through a gentle process, with two objects slowly spiraling together in a low-velocity collision rather than smashing together violently. The fact that it survived intact for billions of years also suggests that the Kuiper Belt, for all its vastness, is a relatively peaceful place compared to the chaotic, collision-prone inner solar system. Yet this peacefulness hides deeper mysteries because Arrokoth's very existence challenges some of our models of how planetary building blocks come together. The composition of Arrokoth's surface revealed even more surprises. Data from New Horizons color imaging and spectroscopic instruments showed that Arrokoth has an unusually reddish hue, likely caused by organic molecules called tholins that form when methane and nitrogen ices are bombarded by cosmic radiation over millions of years. These tholins aren't just pretty colors, they're complex organic compounds, the same kinds of chemistry that might have seeded early Earth with the ingredients necessary for life. So in a very real sense, studying Arrokoth and its kin helps us understand not just where we came from, but how the chemistry of life itself might have originated. If you're enjoying this deep dive into the outer solar system, make sure you hit that subscribe button and give this video a thumbs up. Your support helps this channel grow. Now let's zoom out and consider the bigger picture. The Kuiper Belt isn't just a curiosity for astronomers peering through telescopes. It's also the source of many of the comets that occasionally grace our skies with their glowing tails. These short-period comets, the ones that orbit the Sun in less than 200 years, originate from the Kuiper Belt. Gravitational interactions with Neptune or encounters with other Kuiper Belt objects can nudge these icy wanderers onto new paths, sending them spiraling inward toward the inner solar system. When they approach the Sun, their ices vaporize, creating the spectacular tails that have inspired awe and sometimes terror throughout human history. But comets aren't just beautiful celestial phenomena to admire from a safe distance. They're also potential threats. Throughout Earth's history, comets and asteroids have slammed into our planet with devastating consequences. The most famous example is the impact that occurred 66 million years ago, which contributed to the extinction of the dinosaurs and roughly 75% of all species on Earth. While that particular impactor was likely an asteroid from the inner solar system rather than a Kuiper Belt comet, the principle remains the same. Objects from space can and do collide with Earth, and the Kuiper Belt represents a vast reservoir of potential impactors that we're only beginning to understand. What makes Kuiper Belt comets particularly concerning is their unpredictability. Unlike near-Earth asteroids, which we can track and catalogue with increasing precision, Kuiper Belt objects that get knocked onto Earth-crossing orbits can arrive with little warning. They approach from the outer solar system, often on trajectories we're not monitoring as carefully, and they can be moving at tremendous speeds by the time they reach Earth's neighborhood. Imagine standing on a highway and suddenly seeing a truck barreling toward you from an unexpected direction. That's somewhat analogous to the challenge of detecting and tracking long-period comets originating from the outer reaches of our solar system. Recent studies using the Subaru telescope in Hawaii have added another layer to our understanding of the Kuiper Belt structure and population. By applying unique analysis methods to ultra-wide field images, astronomers have discovered objects that potentially extend the Kuiper Belt region even farther than previous estimates suggested. Two objects in particular, designated 2020 KJ60 and 2020 KK60, have orbits that place them at the outer fringes of what we consider the classical Kuiper Belt. Their discovery raises intriguing questions about where the Kuiper Belt truly ends and where the even more distant Oort cloud begins. The Oort cloud, if you're not familiar, is a theoretical spherical shell of icy bodies thought to surround our entire solar system at distances ranging from thousands to hundreds of thousands of astronomical units from the Sun. While no Oort cloud object has ever been directly observed, they're simply too far away and too faint, astronomers infer its existence from the orbits of long-period comets that take thousands or even millions of years to complete a single trip around the Sun. The boundary between the Kuiper Belt and the Oort cloud remains fuzzy, and discoveries like those from the Subaru telescope help us sketch in the details of this cosmic borderland. Now here's where we need to confront an uncomfortable truth about our knowledge, or rather, our lack thereof. Despite decades of observations and multiple spacecraft missions, we've directly explored only a tiny fraction of the Kuiper Belt. New Horizons flew past Pluto and Arrokoth, giving us up-close looks at two objects, but that's like visiting two houses in a city of millions and claiming to understand the entire metropolis. The vast majority of Kuiper Belt objects remain unvisited, their compositions unknown, their surfaces unmapped, their histories untold. We're making educated guesses based on limited data, and while those guesses are informed by solid physics and chemistry, the Kuiper Belt undoubtedly holds surprises we haven't even imagined yet. Consider the case of Quaoar, another large Kuiper Belt object that's been making headlines recently. Quaoar, which measures roughly 700 miles in diameter, about half the size of Pluto, has a satellite named Quaoar. In 2023, astronomers successfully observed a stellar occultation by Quaoar, which means they watched as Quaoar passed in front of a distant star, blocking its light. By carefully timing how long the star remained hidden and analyzing the observations from multiple locations across North America, scientists were able to constrain Quaoar's size and shape with remarkable precision. They determined that Quaoar's equivalent diameter falls between 116 and 172 kilometers, with a geometric albedo, essentially its reflectivity, between 0.024 and 0.078. That's substantially darker than Quaoar itself, raising fascinating questions about how a satellite and its parent body can have such different surface properties. But Quaoar has another claim to fame that's even more perplexing. Recent observations revealed that Quaoar possesses a ring system similar to Saturn's rings but on a much smaller scale. Here's the kicker. This ring is located beyond Quaoar's Roche limit. The Roche limit is the distance within which a celestial body's tidal forces would tear apart any object held together only by gravity. Inside the Roche limit, you can have rings because any material trying to coalesce into a moon would be ripped apart. Outside the Roche limit, material should clump together to form moons rather than remaining as rings. Yet Quaoar's ring defies this conventional understanding, existing where it theoretically shouldn't. This discovery challenges our models of ring dynamics and suggests we still have much to learn about the physics governing these distant systems. Speaking of challenges to our understanding, if you found this discussion about the outer solar system intriguing, you might want to check out my video called Mars, Maybe as Far as Humans Can Really Go. In that exploration, I delve into the practical and physical barriers that make venturing beyond Mars, let alone reaching the Kuiper Belt, extraordinarily difficult with our current technology. The link is in the description. The Kuiper Belt isn't just distant in terms of miles, it represents a frontier that may remain beyond human reach for generations, if not centuries. Understanding these limitations helps us appreciate just how remarkable our robotic explorers like New Horizons truly are, and why every data point they send back is precious beyond measure. The James Webb Space Telescope, humanity's most powerful space observatory, has also turned its attention to trans-Neptunian objects, revealing details about their ancient surfaces that were impossible to observe before. Webb's infrared capabilities allow it to analyze the chemical composition of these distant worlds with unprecedented precision. Recent observations published in February 2025 showed that many trans-Neptunian objects have surfaces dominated by water ice mixed with methane, nitrogen, and complex organic molecules. These surface materials have remained largely unchanged for billions of years, preserved in the deep freeze of the outer solar system like cosmic fossils. What Webb's observations tell us is that trans-Neptunian objects are incredibly diverse in their compositions, colors, and physical properties. Some are bright and icy, while others are dark and carbon-rich. Some rotate rapidly, completing a spin in just a few hours, while others tumble lazily through space, taking days to complete a single rotation. This diversity reflects the complex history of the solar system's formation and evolution, with each object carrying clues about the conditions in different parts of the primordial disk from which the planets emerged. But diversity isn't the only characteristic that makes the Kuiper Belt fascinating. It's also the sheer scale of the unknown. When New Horizons' student dust counter detected those unexpectedly high dust levels far beyond where models predicted a decline, it wasn't just finding more dust, it was revealing a fundamental gap in our understanding of how the outer solar system is structured. Dust in the Kuiper Belt comes primarily from two sources: collisions between larger Kuiper Belt objects that shatter and pulverize ice and rock, and particles kicked up when microscopic interstellar dust grains pepper the surfaces of these worlds at high velocity. The fact that dust levels remain elevated so far out suggests either that collisions are more common than we thought, or that there are simply more objects out there than our sensors has accounted for. Let's pause and think about what a collision between Kuiper Belt objects actually looks like. These aren't the dramatic, explosive impacts you might see in science fiction movies. Remember, space is almost unimaginably empty, even in regions we describe as crowded. The average distance between Kuiper Belt objects is measured in millions of miles. When collisions do occur, they happen at relatively modest speeds compared to impacts in the inner solar system, because the objects are all moving in roughly the same direction around the Sun, like cars on a cosmic highway. Still, even a low-velocity collision releases tremendous energy when you're dealing with objects that can be tens or hundreds of miles across. The result is fragmentation, with pieces ranging from boulder-sized chunks down to microscopic dust particles, all adding to the debris field that New Horizons is now sampling. This brings us to a troubling possibility that scientists are beginning to seriously consider. The Kuiper Belt might be far more dynamic and chaotic than we previously believed. For decades, the prevailing view held that the Kuiper Belt was a relatively stable, quiet region where objects had settled into peaceful orbits billions of years ago. Sure, occasional gravitational nudges from Neptune might perturb an orbit here or there, sending an unlucky object on a comet-like plunge toward the inner solar system, but overall, the region was thought to be calm and unchanging. The new dust data, combined with observations of unexpected orbital distributions and the discovery of objects in unusual configurations like Quaoar's impossible ring, suggests that this picture might be incomplete. One hypothesis gaining traction is that the Kuiper Belt is still evolving, still reshaping itself through ongoing collisions and gravitational interactions. If true, this has profound implications. It means the Kuiper Belt isn't just a historical record frozen in time, it's an active, living laboratory where primordial processes continue to unfold. It also means that the population of objects capable of becoming comets and potentially threatening Earth might be larger and more dynamic than we've accounted for in our risk assessments. This isn't meant to alarm you unduly. The probability of a Kuiper Belt comet striking Earth in any given year remains extraordinarily low, but it does underscore the importance of continued observation and study. Now let's talk about Pluto for a moment, because no discussion of the Kuiper Belt would be complete without mentioning this controversial world. When New Horizons flew past Pluto on July 14, 2015, it revealed a world of staggering complexity and beauty. Instead of the dead, cratered ice ball many scientists expected, Pluto turned out to be geologically active, with vast plains of nitrogen ice, towering mountains made of water ice as hard as rock at those frigid temperatures, and a surprisingly thin but extensive atmosphere that escapes into space and freezes back onto the surface in a delicate cycle. Pluto's surface tells a story of recent activity, and by recent I mean within the last few million years, which is the blink of an eye in geological terms. The heart-shaped region called Tombor Regio, named after Pluto's discoverer Clyde Tombor, shows no impact craters at all, indicating that it's been resurfaced recently by some internal process. Scientists suspect that Pluto harbors a subsurface ocean of liquid water beneath its icy crust, kept from freezing by radioactive decay in the rocky core, and perhaps by tidal heating from interactions with its large moon Charon. If Pluto, a world so distant that sunlight reaching it is 1,500 times fainter than on Earth, can maintain geological activity and possibly even a subsurface ocean, what does that tell us about other large Kuiper Belt objects? And this question becomes even more intriguing when we consider objects like Eris, another dwarf planet in the Kuiper Belt that's actually slightly more massive than Pluto, or Makemake and Haumea, each with their own peculiar characteristics. Haumea, for instance, spins so rapidly that it's been stretched into an elongated football-like shape, completing a rotation every 4 hours. It also has a ring system and 2 known moons. Makemake, meanwhile, appears to have a moon of its own and shows evidence of methane ice on its surface. Each of these worlds is unique, each has its own story, and collectively they paint a picture of the Kuiper Belt as a region of remarkable diversity and complexity. But here's where the terrifying part comes in. Not terrifying in a monsters and mayhem sense, but terrifying in terms of the cosmic perspective it forces upon us. The Kuiper Belt represents the edge of what we can reliably observe and study with current technology. Beyond it lies the vast, largely unexplored realm of the Oort cloud, and beyond that the incomprehensible emptiness of interstellar space, stretching to the nearest stars. When you contemplate the Kuiper Belt, you're forced to confront the sheer scale of the universe and our infinitesimal place within it. Our entire civilization, every human who has ever lived, every thought ever thought and deed ever done, has occurred on a pale blue dot orbiting within the inner solar system, a region that represents less than 1% of the volume of space influenced by our sun's gravity. The Kuiper Belt also reminds us of our vulnerability. Those objects out there, orbiting peacefully in the cold and dark, are potential impactors. The comets that originate there have struck Earth in the past and will strike again in the future. It's not a matter of if, but when. The question is whether we'll have developed the technology and infrastructure to detect and deflect such threats before they arrive. Recent efforts like NASA's DART mission, which successfully altered the orbit of a small asteroid in 2022, demonstrate that we're making progress on planetary defense, but deflecting a long-period comet from the Kuiper Belt would present challenges an order of magnitude more difficult than nudging a near-Earth asteroid. Consider the physics involved. A Kuiper Belt comet nudged onto an Earth-crossing orbit might take decades or even centuries to arrive, but detecting it early requires constantly monitoring the entire sky for faint, moving objects, a monumental task. Once detected, the comet would be approaching at speeds of 30 to 50 kilometers per second or even faster. Intercepting such an object to deflect it would require launching a mission years in advance, precisely calculating the comet's trajectory and delivering enough energy to alter its path by the tiny fraction needed to make it miss Earth. And we'd need to do all this for an object whose composition and structure we might know very little about until our deflection attempt was already underway. This isn't science fiction, it's the reality of living in a solar system filled with debris left over from its formation. The Kuiper Belt, for all its beauty and scientific value, is also a reminder that space is not an entirely benign environment. It's a place governed by gravity, momentum, and chance, where objects billions of years old follow paths determined by the gravitational dance of the planets, and where a slight perturbation at the right moment can send a mountain of ice and rock hurtling toward the inner solar system. Yet there's also something profoundly inspiring about the Kuiper Belt. It represents a frontier, a place where exploration is still in its infancy and where every new discovery has the potential to reshape our understanding. When Gerard Kuiper first proposed the existence of this belt in 1951, it was pure speculation based on theoretical considerations. Now we've confirmed the existence of thousands of objects there, flown spacecraft past 2 of them, and used powerful telescopes to analyze their compositions and orbits. In less than a century, we've gone from wondering whether the Kuiper Belt existed to actively exploring it. This progress speaks to the power of human curiosity and ingenuity. We're a species that looks up at the night sky and asks questions. We build telescopes and spacecraft, develop mathematical models and computer simulations, and slowly, painstakingly piece together the story of our cosmic origins. The Kuiper Belt is part of that story, a crucial chapter that helps us understand not just where the solar system came from, but where it might be going. One of the most profound insights from studying the Kuiper Belt concerns the formation of planets themselves. The prevailing theory, developed over decades of observation and refinement, suggests that planets form through a process called accretion. It starts with microscopic dust grains in the protoplanetary disk around a young star. These grains stick together through electrostatic forces and gentle collisions, gradually building up into pebbles, then rocks, then boulders. Eventually, some of these growing planetesimals become massive enough that their gravity dominates, allowing them to sweep up material from their orbital neighborhoods and grow into full-fledged planets. The Kuiper Belt represents the leftovers from this process, the material that never quite made it into a planet. Out beyond Neptune, the protoplanetary disk was so sparse and the orbital period so long that accretion proceeded incredibly slowly. Before a planet could form in that region, the gas from the primordial solar nebula dissipated, and the remaining solid material was simply too spread out to coalesce efficiently. What we're left with is a population of objects frozen in various stages of growth, from tiny fragments up to dwarf planets like Pluto and Eris that came tantalizingly close to achieving full planetary status, but never quite made it. Arrokoth's gentle merger tells us something beautiful about this process. When New Horizons revealed that Arrokoth formed through the soft collision of two separate lobes, it confirmed theoretical predictions about how planetesimals in the outer solar system came together. The encounter wasn't violent. There were no catastrophic impacts that shattered both objects into fragments. Instead, two bodies that had been orbiting each other in a gravitational dance slowly spiraled inward, perhaps influenced by drag from the thinning gas of the solar nebula, until they touched and stuck together. This gentle process preserved the delicate structures on both lobes, allowing them to survive intact for over 4 billion years. But here's the unsettling part. While Arrokoth represents successful, gentle accretion, it's also an exception. Most objects in the Kuiper Belt show evidence of more violent histories. Impact craters pepper their surfaces, testament to billions of years of collisions with smaller debris. Some objects are fragments from larger bodies that were catastrophically disrupted. Others have been gravitationally scattered by Neptune, their orbits flung into elongated, tilted paths that bear little resemblance to the circular, flat orbits they likely started with. The Kuiper Belt, in other words, is both a nursery and a graveyard, a place where worlds were born and where many of them met violent ends. This duality makes the Kuiper Belt a natural laboratory for studying planetary formation and destruction in ways that are impossible in the inner solar system. The terrestrial planets, Mercury, Venus, Earth, and Mars, have been so thoroughly modified by billions of years of geological activity, weathering, and in Earth's case, life itself, that they've lost most traces of their primordial compositions and structures. The Kuiper Belt objects, by contrast, have been preserved in deep freeze, their surfaces and interiors remaining largely unchanged since the solar system's youth. Recent analysis using the James Webb Space Telescope has provided unprecedented detail about what these ancient surfaces are made of. In February 2025, astronomers published findings revealing that trans-Neptunian objects display a remarkable variety of surface compositions. Some are dominated by water ice, which appears bright and reflective in Webb's infrared observations. Others show strong signatures of methane ice, which can appear in different crystalline forms depending on temperature and pressure history. Still others display complex organic compounds, those tholins I mentioned earlier, that give them distinctly reddish colors. What's particularly fascinating is that objects with similar orbits and presumably similar formation histories can have completely different surface compositions. This suggests that even small differences in initial conditions, perhaps the ratio of rock to ice, or the specific mix of volatile compounds incorporated during formation, can lead to dramatically divergent evolutionary paths. Two objects born as neighbors might end up looking completely different after billions of years, one bright and icy, the other dark and organic-rich, depending on factors we're only beginning to understand. Temperature plays a crucial role in this evolution. Even though the Kuiper Belt is extraordinarily cold by human standards, surface temperatures hover around -390 degrees Fahrenheit or -235 degrees Celsius, there are subtle temperature variations that matter on these timescales. An object closer to the Sun experiences slightly higher temperatures than one farther out, and this difference can determine whether certain volatile ices remain frozen on the surface or sublimate away into space over billions of years. Objects with darker surfaces absorb slightly more of the already faint sunlight, warming just enough to potentially lose their most volatile ices while retaining others. These feedback loops create the diversity we observe. Now let's consider what happens when one of these objects gets perturbed onto a new orbit that brings it closer to the Sun. As it enters the region inside Neptune's orbit, it begins its transformation into what we recognize as a comet. The increasing solar radiation warms the surface, causing volatile ices to sublimate, that is, to transition directly from solid to gas without becoming liquid. This gas streams away from the nucleus, carrying dust particles with it and creating the characteristic coma, the fuzzy envelope surrounding the comet's solid nucleus, and eventually the spectacular tail that can stretch for millions of miles. What we see when we observe a comet is actually a tiny fraction of its total mass. The nucleus might be a few miles across, but the coma can swell to hundreds of thousands of miles in diameter, and the tail can extend for tens of millions of miles. Yet all that impressive display comes from the sublimation of surface ice on a relatively small, dirty snowball from the Kuiper Belt. It's a reminder that even modest-sized objects can create impressive phenomena under the right conditions. But comets do more than just put on a show. They also deliver material to the inner solar system, including potentially to Earth. Every time a comet passes near the Sun, it loses mass through sublimation. Some of this material falls back onto the comet's nucleus, but much of it disperses into space, spreading along the comet's orbital path. When Earth crosses the orbit of a comet, we plow through this debris stream, and the particles burn up in our atmosphere, creating meteor showers. The Perseids in August, the Leonids in November, the Geminids in December, these annual celestial displays are caused by Earth encountering debris from specific comets. More significantly, comets may have played a crucial role in delivering water and organic compounds to the early Earth. Our planet formed in a region of the solar system that was too hot for water ice to condense directly from the protoplanetary disk. The water in Earth's oceans, the water in your body right now, had to come from somewhere. One hypothesis suggests that much of it arrived via impacts from water-rich asteroids and comets during a period called the Late Heavy Bombardment, roughly 4 billion years ago. If this is true, then the Kuiper Belt didn't just give us meteor showers and spectacular cometary displays. It gave us the oceans themselves and possibly the organic chemistry that led to life. This connection between the Kuiper Belt and the origin of life on Earth is speculative but tantalizing. When we analyze the organic compounds found in comets and on Kuiper Belt objects like Arrokoth, we find molecules that are chemically similar to the building blocks of life: amino acids, nucleotide bases, and other complex carbon-containing compounds. These molecules aren't life, but they're the raw ingredients from which life could emerge given the right conditions. The idea that the seeds of life might have been delivered from the frozen outer reaches of the solar system adds a poetic dimension to our exploration of the Kuiper Belt. Yet this poetic connection also carries a darker implication. If comets from the Kuiper Belt delivered the ingredients for life, they've also delivered catastrophic destruction throughout Earth's history. The same process that might have seeded our planet with water and organics has also periodically bombarded it with devastating impacts. The geological record preserves evidence of numerous impact events, some of which coincide with mass extinctions. While the most famous extinction event, the one that ended the age of dinosaurs 66 million years ago, was likely caused by an asteroid rather than a comet, the potential for a large Kuiper Belt comet to strike Earth remains a sobering reality. What makes cometary impacts particularly concerning is the speed at which they arrive. Asteroids from the inner solar system typically impact Earth at velocities between 11 and 20 kilometers per second. Long-period comets from the Kuiper Belt, or Oort cloud, can arrive at speeds exceeding 70 kilometers per second. The kinetic energy of an impact scales with the square of the velocity, meaning that a comet striking at 70 kilometers per second delivers more than 12 times the energy of an asteroid of the same mass hitting at 20 kilometers per second. This enormous energy release can have global consequences, potentially triggering climate changes, wildfires, and ecological collapse on a planetary scale. Fortunately, large cometary impacts are rare. We're talking about timescales of millions of years between truly catastrophic events. But rare doesn't mean impossible, and the consequences of even a moderate-sized impact would be severe enough to justify our efforts to detect and track potential threats. This is why missions like New Horizons and telescopic surveys of the Kuiper Belt aren't just about satisfying scientific curiosity, they're about understanding the population of objects that could, under the right circumstances, become existential threats to civilization. Speaking of New Horizons, let's appreciate for a moment just how remarkable this mission has been. Launched on January 19, 2006, New Horizons is currently the fastest human-made object ever to leave Earth, having departed our planet at a speed of roughly 36,000 miles per hour. It flew past Jupiter in February 2007, using the giant planet's gravity to slingshot even faster toward its primary target, Pluto. After more than 9 years of interplanetary travel covering over 3 billion miles, New Horizons reached Pluto on July 14, 2015, becoming the first spacecraft to explore this distant world up close. But the mission didn't end there. After Pluto, the New Horizons team used the Hubble Space Telescope to search for a suitable secondary target, something the spacecraft could reach with its remaining fuel. That search led to the discovery and selection of Arrokoth, which New Horizons encountered on New Year's Day, 2019. The spacecraft is now continuing its journey outward, sending back data about the environment of the Kuiper Belt itself, including those intriguing dust measurements we discussed earlier. As of May 2026, New Horizons is approximately 58 astronomical units from the Sun. That's about 5.4 billion miles, and it's still functioning, still transmitting, still exploring. The longevity and success of New Horizons represents a triumph of engineering and human determination. The spacecraft operates in an environment where sunlight is so weak that solar panels would be useless, so it's powered instead by a radioisotope thermoelectric generator, essentially a nuclear battery that converts heat from decaying plutonium-238 into electricity. The extreme cold of the outer solar system means that components must be carefully designed to withstand temperatures that would cause most materials to become brittle and fail. Communication with Earth requires powerful antennas and exquisite timing because radio signals take over 8 hours to travel from New Horizons to Earth at its current distance. Every image, every spectrum, every dust count that New Horizons sends back represents not just data, but a testament to human ingenuity. We built a machine capable of surviving and functioning in one of the most hostile environments imaginable, sent it on a journey lasting decades, and successfully guided it past targets with precision measured in minutes and miles despite the vast distances involved. When you look at an image of Arrokoth or read about the dust measurements from the Kuiper Belt, you're witnessing the fruits of countless hours of work by engineers, scientists, programmers, and technicians who dedicated years of their lives to pushing the boundaries of exploration. This brings me to a critical point about the Kuiper Belt and scientific exploration more generally. We're still in the early stages of understanding this region. New Horizons has visited 2 objects out of potentially hundreds of thousands or even millions. Ground-based and space-based telescopes have catalogued a few thousand Kuiper Belt objects, but most of them appear as nothing more than faint points of light in our most powerful instruments. We can measure their orbits, estimate their sizes, and in some cases determine their approximate compositions from spectroscopy, but we lack the detailed, close-up observations that would reveal their true natures. This is where the terrifying aspect of the Kuiper Belt becomes most apparent, the vast unknown. For all we've learned, we remain profoundly ignorant about this region. We don't know the exact size distribution of objects, how many there are at different scales from dust particles to dwarf planets. We don't fully understand the collisional history and how it's shaped the population over billions of years. We have competing theories about the dynamical evolution of the Kuiper Belt and how Neptune's migration affected it, but limited observations to test these theories rigorously. We're uncertain about where the Kuiper Belt ends and other structures like the scattered disk or the Oort cloud begin. This uncertainty extends to fundamental questions about solar system formation. Why did planet formation stop at Neptune? Why didn't a large planet form in the Kuiper Belt region, consolidating all that material into a single world? The answer likely involves the low density of material at such distances and the long orbital periods that slow down accretion. But the details remain debated. Some scientists have even proposed that a large planet, sometimes called Planet 9 or Planet X, might exist in the outer solar system, shepherding the orbits of certain Kuiper Belt objects through gravitational influence. Searches for this hypothetical planet have so far come up empty, but the orbital patterns that inspired the hypothesis remain unexplained. The Planet 9 hypothesis illustrates how much we still have to learn. If a planet roughly 5 to 10 times Earth's mass exists in the outer solar system, orbiting hundreds of astronomical units from the Sun, it would represent one of the most significant astronomical discoveries of the century. Yet detecting such an object is extraordinarily difficult. At those distances, even a planet would appear incredibly faint, reflecting only a tiny fraction of the already weak sunlight. It would move slowly across the sky, making it hard to distinguish from background stars without years of patient observation. Several telescopic surveys are currently searching for Planet 9, scanning the sky methodically, but the search space is enormous and the chances of success uncertain. Whether or not Planet 9 exists, the search for it exemplifies the detective work that characterizes modern astronomy. Scientists notice patterns in the data, in this case unusual clustering, in the orbits of certain extreme trans-Neptunian objects, and develop hypotheses to explain those patterns. They make predictions based on their hypotheses, then design observations to test those predictions. Sometimes the hypotheses are confirmed, sometimes they're refuted, and sometimes the results are ambiguous, requiring further investigation. This is how science progresses, not through sudden flashes of insight, but through the patient accumulation of evidence and the careful testing of ideas. The Kuiper Belt rewards this patient approach. Every new observation, every new discovery adds another piece to the puzzle. When astronomers detected higher than expected dust levels with New Horizons, it didn't immediately answer questions. It raised new ones. Is there a second belt? Does the main belt extend farther? Are collisions more frequent than we thought? These questions drive new observations, new theoretical work, and eventually deeper understanding. Science is a process, not a destination, and the Kuiper Belt represents one of the frontiers where this process is most actively unfolding. Let's also consider the role of technology in enabling these discoveries. The Kuiper Belt was invisible to ancient astronomers who could only observe with their unaided eyes. It remained invisible even after the invention of telescopes because the objects are too faint and too distant. It wasn't until the development of electronic detectors, CCDs, and later more advanced sensors that astronomers gained the sensitivity needed to detect Kuiper Belt objects. And it wasn't until the space age that we could send spacecraft to actually visit these worlds and observe them up close. Each technological advance opens new windows of discovery. The Hubble Space Telescope, launched in 1990, revolutionized our view of the Kuiper Belt by detecting numerous faint objects that ground-based telescopes struggled to find. The Atacama Large Millimeter Array, or ALMA in Chile, has allowed astronomers to study the dust and gas around other stars, revealing protoplanetary disks that resemble what our solar system might have looked like during its formation, providing context for understanding how our own Kuiper Belt came to be. And now the James Webb Space Telescope is delivering infrared observations of unprecedented quality, revealing the compositions of distant Kuiper Belt objects with a clarity that was impossible just a few years ago. But technology doesn't just enable passive observation, it also allows active exploration. Spacecraft like New Horizons carry instruments specifically designed to answer questions about the Kuiper Belt. The Long-Range Reconnaissance Imager, or LORRI, captures high-resolution photographs that reveal surface features. The RALPH instrument combines visible and infrared spectrometers to analyze surface compositions. The Student Dust Counter measures the density and distribution of dust particles. The radio science experiment uses the spacecraft's communication system to measure masses and search for atmospheres. Together, these instruments transform a flyby lasting just hours into a treasure trove of data that scientists will analyze for years. Yet for all our technological prowess, we remain constrained by the laws of physics and the practical limitations of engineering and economics. Sending a spacecraft to the Kuiper Belt requires enormous velocities to cover the vast distances in a reasonable time frame, and achieving those velocities demands powerful rockets and efficient trajectories. New Horizons benefited from a gravity assist at Jupiter, but even so, the journey to Pluto took 9.5 years. Any future mission to explore more of the Kuiper Belt faces similar time constraints, meaning that mission planners, engineers, and scientists must commit to projects that will span decades from conception to completion. This long-term commitment represents both a challenge and an inspiration. The scientists who proposed New Horizons in the early 2000s knew they might be retiring by the time the spacecraft reached its destination. Some of the engineers who built it have passed away, never seeing the final results of their labor. Yet they persevered, driven by curiosity and the knowledge that their work would expand human understanding, even if they themselves might not live to see all the fruits of their efforts. There's something profoundly moving about this intergenerational dimension of space exploration. We plant trees whose shade we may never sit under, building knowledge for the benefit of future generations. Now let's shift perspective and think about what the Kuiper Belt tells us about other solar systems. For decades, our solar system was the only one we knew, and we naturally assumed it was typical. But the discovery of exoplanets, planets orbiting other stars, beginning in the 1990s, has revealed astonishing diversity. Some systems have giant planets orbiting closer to their stars than Mercury orbits our Sun. Others have planets in configurations completely unlike anything in our solar system. This diversity raises an important question. Is our Kuiper Belt typical, or is it unusual? The answer appears to be that debris disks around other stars are common, but they vary widely in their properties. Many stars, especially young ones, show infrared excess, extra infrared radiation that comes from dust in a disk surrounding the star. This dust is thought to be analogous to the dust in our Kuiper Belt, constantly replenished by collisions between larger bodies. Observations with ALMA and other telescopes have revealed exquisite details in some of these disks, including gaps, rings, and asymmetries that hint at the gravitational influence of unseen planets. One of the most famous examples is the disk around the star Beta Pictoris, located roughly 63 light-years from Earth. This young star, only about 23 million years old, is surrounded by a prominent debris disk that we see nearly edge-on. High-resolution observations have revealed warps and asymmetries in the disk, and astronomers have directly imaged at least 2 giant planets orbiting within it. The Beta Pictoris system provides a glimpse of what our own solar system might have looked like in its youth, when the Kuiper Belt was likely much denser and collisions more frequent, creating more dust and potentially spectacular cometary displays. Another intriguing system is Fomalhaut, a bright star visible to the naked eye from the southern hemisphere, located about 25 light-years away. Fomalhaut is encircled by a narrow, well-defined ring of dust that's offset from the star itself, a configuration that strongly suggests the gravitational influence of one or more planets shepherding the debris into this particular arrangement. Observations of Fomalhaut's disk have revealed what might be a planet, though its nature remains controversial and debated in the scientific literature. Regardless of the details, Fomalhaut demonstrates that debris disks, and by extension Kuiper Belt analogues, are not rare oddities but common features of planetary systems. These observations of other systems inform our understanding of our own Kuiper Belt by providing comparative context. They show us that the process that created our Kuiper Belt, planet formation, leaving behind a debris disk of leftover material, is a natural outcome of how solar systems form. They also suggest that the structure and evolution of these disks depend sensitively on the configuration of planets in the system. A system with different giant planets in different orbits might have a debris disk that looks quite unlike our Kuiper Belt, either more massive, less massive, at a different distance, or with a different structure. This comparative perspective also makes the Kuiper Belt less terrifying in one sense. It's a natural, expected component of planetary systems, not some bizarre anomaly unique to us. But it also reinforces the terrifying aspects by showing us just how common these reservoirs of impactors are throughout the galaxy. Every planetary system likely has its own version of the Kuiper Belt, which means that any planets in those systems face the same risks of impacts that Earth does. If life exists elsewhere in the universe, and the sheer number of planets suggests it probably does, then that life has also had to contend with bombardment from its own Kuiper Belt analogues. Let's return to our own solar system and consider what the future holds for the Kuiper Belt. On timescales of millions to billions of years, the Kuiper Belt will continue to evolve. Collisions will grind down objects into smaller pieces. Neptune's gravity will continue to perturb orbits, occasionally sending objects into the inner solar system or ejecting them from the solar system entirely. The Sun itself will eventually exhaust its hydrogen fuel and begin evolving off the main sequence, swelling into a red giant and eventually shedding its outer layers to form a planetary nebula, leaving behind a white dwarf remnant. What happens to the Kuiper Belt during this stellar evolution remains somewhat speculative, but we can make educated guesses. As the Sun expands into a red giant, perhaps 5 billion years from now, its luminosity will increase dramatically, and even objects in the Kuiper Belt will experience significantly higher temperatures. Volatile ices that have remained frozen for billions of years will sublimate away. Some objects might develop coma and tails, effectively becoming comets despite never leaving their original orbits. The increased solar wind during the red giant phase might also strip away material from these objects, gradually eroding them over millions of years. Eventually, when the Sun sheds its outer layers and contracts to become a white dwarf, the Kuiper Belt objects will find themselves orbiting a star that's much dimmer and cooler than the Sun today. The objects will freeze even more thoroughly than they are now, their surfaces dropping to temperatures only a few degrees above absolute zero. Those that survive the red giant phase, and many will because they're far enough away to avoid being engulfed, will continue their slow orbits around the white dwarf for trillions of years, gradually spreading out as their orbits are perturbed by passing stars and the overall evolution of the galaxy. This cosmic perspective, contemplating the fate of the Kuiper Belt billions of years hence, might seem disconnected from our immediate concerns, but it's part of what makes astronomy so profound. We're studying objects and processes that span timescales vastly longer than human civilization, longer even than life has existed on Earth. The Kuiper Belt has been out there for 4.6 billion years, silently orbiting, occasionally flinging a comet our way, preserving in its icy embrace the memory of our solar system's birth. And it will likely still be there, in some form, when our Sun dies and the planets are consumed or frozen into eternal darkness. Consider for a moment the sheer audacity of what we've accomplished. In the span of just over a century, humanity went from the Wright brothers' 12-second flight at Kitty Hawk to landing robots on Mars and flying spacecraft past Pluto and Arrokoth. Our grandparents' generation witnessed both the first airplane flights and the first moon landing. We're living through the era when our species is actively exploring the Kuiper Belt, not just observing it from afar, but actually sending emissaries to visit these distant worlds and report back what they find. This rapid progress can make it easy to take for granted just how extraordinary it is. But pause and really think about it. We sent a machine weighing about 1,000 pounds to a target smaller than a city, located more than 4 billion miles away, traveling at over 30,000 miles per hour, and we hit it. The precision required is staggering. It's like shooting an arrow from New York and hitting a specific window in Los Angeles, except the target is moving, you're moving, and you have to calculate where the target will be years in advance, because that's how long your arrow takes to arrive. This precision wasn't achieved through luck, but through mathematics, physics, engineering, and careful planning. It required understanding orbital mechanics well enough to predict planetary positions years in advance. It demanded spacecraft systems robust enough to function for decades in the harsh environment of space. It necessitated communication systems capable of receiving whisper-faint signals from billions of miles away and interpreting them correctly. Every aspect of the New Horizons mission to Arrokoth represented accumulated human knowledge refined over centuries of scientific progress. Yet even with all this capability, our exploration of the Kuiper Belt remains in its infancy. We visited 2 objects up close and observed a few thousand from afar out of a population that likely numbers in the millions or even billions. It's like trying to understand Earth's entire biosphere after examining 2 animals and glimpsing a few thousand others as distant specks. We can draw some conclusions, make some inferences, but vast uncertainties remain. These uncertainties manifest in concrete ways. For instance, we still don't have a complete inventory of potentially hazardous objects from the Kuiper Belt. Most long-period comets, those with orbital periods greater than 200 years, originate from either the Kuiper Belt or the more distant Oort cloud, but we typically don't detect them until they've already entered the inner solar system and begun developing their characteristic coma. By the time we spot them, there's limited time to study their orbits and determine whether they might pose a threat to Earth on their current pass or during future returns. This detection problem is particularly acute for objects approaching from the direction of the Sun, which can remain hidden in solar glare until they're relatively close. In 2013, a small asteroid about 20 meters in diameter, not from the Kuiper Belt, but the principle applies, exploded over Chelyabinsk, Russia, releasing energy equivalent to approximately 500 kilotons of TNT. The explosion shattered windows across a wide area and injured over 1,500 people. We had no advance warning because the object approached from the sunward direction and was too small to be detected by our current survey systems. Now imagine a Kuiper Belt object several kilometers in diameter on a trajectory toward Earth. If we detect it years or decades in advance, we might have options. Send spacecraft to study it, calculate its precise trajectory, and if necessary, attempt deflection using various techniques that have been proposed, kinetic impactors, gravity tractors, or more exotic methods. But if we only detect it months before impact, our options become severely limited. The kinetic energy of such an impact would be devastating on a continental or even global scale, potentially causing mass extinctions and civilizational collapse. The probability of such an event occurring during any given human lifetime is extremely low. We're talking about timescales of millions of years between truly catastrophic impacts. But extremely low probability isn't the same as impossible, and the consequences would be so severe that even a very small probability deserves serious attention. This is why planetary defense, detecting, tracking, and potentially deflecting hazardous objects has become an increasingly important priority for space agencies around the world. NASA's Planetary Defense Coordination Office, established in 2016, works to detect and track near-Earth objects and coordinate response efforts. The European Space Agency has similar programs, and in September 2022, NASA successfully executed the DART mission double asteroid redirection test, which deliberately crashed a spacecraft into the small asteroid moon Dimorphos, changing its orbit around the larger asteroid Didymos. This mission proved that kinetic impactors can work as a deflection technique, at least for smaller objects. But deflecting something massive from the Kuiper Belt would present far greater challenges. This brings us back to the terrifying beauty of the Kuiper Belt. It's beautiful because it represents the preserved history of our solar system, because it contains scientific treasures that teach us about planetary formation, because it occasionally sends us spectacular comets that have inspired humans for millennia. It's terrifying because it's a vast reservoir of potential impactors, because we know so little about it despite our progress, and because it reminds us that we inhabit a dynamic, sometimes violent universe where catastrophic events are not just possible, but inevitable given enough time. Living with this knowledge requires a kind of mature cosmic perspective. We can't eliminate risk. The universe doesn't offer perfect safety. But we can work to understand and mitigate threats while still appreciating the wonder of what we're studying. The Kuiper Belt doesn't become less scientifically fascinating because some of its objects might someday threaten Earth. If anything, that possibility makes understanding the region even more important. Let's also consider what future exploration might reveal. Each new mission to the Kuiper Belt, each improved telescope survey, has the potential to overturn our current understanding. Science progresses not just through accumulation of expected results, but through surprises, observations that don't fit existing theories and force us to rethink our assumptions. The Kuiper Belt has already surprised us multiple times. The sheer number and diversity of objects exceeded early predictions. Pluto's complex geology and atmosphere were unexpected. Arrokoth's bilobate structure and gentle formation contradicted assumptions about violent early solar system evolution. And the dust measurements suggesting additional structure have challenged our models of the region's architecture. What other surprises await? Perhaps there are object types we haven't yet discovered, compositions or structures that don't fit our current classification schemes. Perhaps the detailed collisional history is more complex than we imagine, with periodic upheavals caused by resonances or external perturbations. Perhaps there are gravitational effects from a yet undetected planet or even a compact object like a primordial black hole, a highly speculative but occasionally proposed explanation for some orbital anomalies. Each discovery, expected or surprising, adds to our understanding. There's also the question of what lies beyond the Kuiper Belt. The region we've been discussing, the classical Kuiper Belt, from roughly 30 to 50 astronomical units, is just the beginning of the outer solar system. Beyond it lies the scattered disk, a region of objects on highly eccentric and inclined orbits, likely scattered there by gravitational interactions with Neptune. Objects like Eris and Sedna occupy this region, following orbits that take them from relatively close to the Sun, though still far beyond Neptune, to distances of hundreds of astronomical units. And beyond the scattered disk, at distances of thousands to tens of thousands of astronomical units, lies the hypothesized Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system. While we've never directly observed the Oort cloud, the objects are simply too far away and too faint, its existence is inferred from the orbits of long-period comets that fall into the inner solar system from all directions, not just from the ecliptic plane where the Kuiper Belt resides. The Oort cloud likely contains trillions of objects far outnumbering the Kuiper Belt and extends perhaps halfway to the nearest star. Think about that for a moment. The boundary of the Sun's gravitational influence, the edge of the solar system, might extend 2 light-years from the Sun nearly halfway to Proxima Centauri, our nearest stellar neighbor, at 4.2 light-years. At such distances, the Sun would appear as merely a bright star, indistinguishable to the eye from other bright stars. Objects in the outer Oort cloud would be more influenced by the gravitational tide from the galaxy as a whole than by the Sun itself. They represent the frontier of what we can meaningfully call our solar system. The existence of this vast halo of material surrounding our solar system has profound implications. First, it means that the solar system is far larger than most people realize. When we see diagrams showing the Sun and planets, they typically end at Neptune or maybe Pluto, giving the impression that the solar system has clear, relatively nearby boundaries. But if we include the Kuiper Belt, scattered disk, and Oort cloud, the solar system extends thousands of times farther than those simple diagrams suggest. We live not in a compact arrangement of planets, but in a vast volume of space containing countless objects, most of which we've never seen and never will. Second, the Oort cloud and outer reaches of the solar system represent a reservoir from which comets are periodically perturbed into the inner solar system by gravitational disturbances. These disturbances can come from several sources, passing stars that wander close enough to the solar system to gravitationally nudge Oort cloud objects, the gravitational tide from the Milky Way galaxy itself, or potentially encounters with molecular clouds as the solar system orbits through the galaxy. Each of these perturbations can send showers of comets falling sunward, temporarily increasing the flux of these objects through the inner solar system. Some researchers have proposed that periodic increases in comet impacts might correlate with mass extinctions in Earth's fossil record. The hypothesis is controversial and not widely accepted, but it's based on the observation that the solar system oscillates above and below the galactic plane as it orbits the galaxy, potentially encountering regions of higher stellar density or molecular cloud material that could disturb the Oort cloud. If such a correlation exists, it would mean that Earth's biological history has been influenced not just by local events, but by our solar system's journey through the galaxy, a connection between life on Earth and galactic dynamics that would be both humbling and terrifying. Whether or not that specific hypothesis is correct, the broader point stands. We're embedded in a vast cosmic environment that influences conditions on Earth in ways we're only beginning to understand. The Kuiper Belt and Oort cloud aren't isolated from the rest of the galaxy. They interact with it through gravity and occasional physical encounters. Our solar system isn't a closed system but an open one, exchanging material and energy with the larger galactic environment over billions of years. This perspective encourages us to think about our place in the cosmos differently. We often think of Earth as isolated, protected by the vast empty spaces of the solar system. And to be fair, space is indeed mostly empty. The distances between objects are enormous compared to the sizes of the objects themselves. But over geological and astronomical timescales, these vast distances don't provide perfect isolation. Impacts happen, comets arrive, stars pass nearby, the galaxy evolves. We're part of a dynamic system that operates on timescales far longer than human experience, but that doesn't mean we're exempt from its effects. Now let's bring this back to something more tangible. What can individuals do with this knowledge? For most people, the Kuiper Belt remains an abstraction, something to read about but not directly experience. You can't visit it yourself, at least not with current technology, and its effects on daily life are imperceptible except during the rare occasions when a comet becomes visible in the sky. Does it matter whether people know about the Kuiper Belt, understand its significance, or appreciate its terrifying beauty? I would argue yes, it does matter for several reasons. First, an informed public is more likely to support continued space exploration and planetary defense efforts. When people understand what the Kuiper Belt is and why it's important, they're more likely to support funding for missions like New Horizons or for survey telescopes that search for potentially hazardous objects. Democracy works best when citizens can make informed decisions about priorities and resource allocation, and that requires basic scientific literacy. Second, learning about the Kuiper Belt and the broader cosmos cultivates a sense of perspective that can be psychologically and philosophically valuable. In our daily lives, we often get caught up in immediate concerns, work stress, relationship problems, financial worries that can feel overwhelming. Stepping back to contemplate the Kuiper Belt, with its ancient ice preserving memories of the solar system's birth, with its slow orbital rhythms spanning centuries and millennia, can provide perspective on our temporary troubles. This doesn't make those troubles less real or less important, but it can help us see them in context. Third, there's intrinsic value in understanding reality as it actually is, rather than as we might wish it to be. The universe doesn't care about human comfort or convenience. It operates according to physical laws that existed before we appeared and will continue after we're gone. The Kuiper Belt exists whether we acknowledge it or not. Comets will occasionally enter the inner solar system regardless of whether we're watching for them. We can choose to remain ignorant of these facts, but ignorance doesn't provide protection. It just leaves us unprepared. This brings me to a point about education and communication. One of the challenges in conveying the significance of the Kuiper Belt, or any astronomical topic, is making it relevant and engaging to people whose daily lives don't involve contemplating cosmic distances or orbital mechanics. Numbers like 4 billion miles or 4.6 billion years are so far outside human experience that they become meaningless abstractions. How do we bridge this gap between the cosmic and the human? One approach is through storytelling. Humans are naturally drawn to narratives, and the exploration of the Kuiper Belt provides rich material for compelling stories. The journey of New Horizons, conceived in the late 1990s, launched in 2006, reaching Pluto in 2015, and Arrokoth in 2019, is an epic spanning decades and involving thousands of people. The scientists who dedicated their careers to making these missions happen, the engineers who solved countless technical challenges, the operators who guided spacecraft across billions of miles, these are human stories that can make abstract astronomical concepts feel more concrete and meaningful. Another approach is through imagery. The pictures of Pluto and Arrokoth captured by New Horizons aren't just data points, They're windows into alien worlds, revealing landscapes unlike anything on Earth. When you look at an image of Arrokoth, you're seeing a place that's really out there, a physical object with its own history and characteristics, not just an abstract concept. These images engage our visual systems in ways that numbers and equations cannot, making distant places feel more real and immediate. But even with storytelling and imagery, there's something irreducibly challenging about truly grasping the scale and significance of the Kuiper Belt. It requires a kind of imaginative leap, the willingness to accept that reality extends far beyond immediate sensory experience, that there are places and timescales and processes utterly unlike anything in daily life, and that these distant phenomena are nonetheless real and worthy of attention and respect. This imaginative leap is, I think, one of the great gifts that science offers. It's not just a collection of facts and theories, but a way of engaging with reality that expands our horizons beyond the immediate and familiar. When you learn about the Kuiper Belt, you're not just memorizing information, you're training your mind to think on larger scales, to appreciate complexity and nuance, to hold uncertainty while still making progress toward understanding. These cognitive skills transfer to other domains, making us better equipped to handle the complexities of modern life. Let me also address a common misconception about the Kuiper Belt and scientific knowledge more generally. The idea that scientists have everything figured out, or that textbooks present complete, final truth. Nothing could be further from reality. Science is characterized not by certainty, but by ongoing revision in light of new evidence. The picture of the Kuiper Belt I presented in this discussion represents our current best understanding based on available evidence, but that understanding will certainly change as we gather more data. This is a feature, not a bug. Science progresses precisely because it's willing to revise conclusions when new evidence emerges. The scientific method isn't about achieving perfect certainty, but about building increasingly accurate and comprehensive models of reality through iterative cycles of observation, hypothesis formation, testing, and revision. The Kuiper Belt our grandchildren learn about will likely differ in significant ways from the one we know today, just as our current understanding differs from what scientists believed in the 1980s before the first Kuiper Belt objects were discovered. This progressive refinement of knowledge should be celebrated rather than seen as a weakness. It means that there's always more to discover, always new questions to ask, always opportunities for the next generation of scientists to make contributions that advance our understanding. The Kuiper Belt isn't a closed book, but an ongoing story, and we're living through one of its most exciting chapters, the transition from remote observation to actual exploration. As we approach the conclusion of this exploration of the Kuiper Belt's terrifying beauty, it's worth reflecting on what we've covered. We've journeyed from the basic definition and structure of this distant region through its role in solar system formation, its potential threats to Earth, its spectacular cometary gifts, and the remarkable human achievements in exploring it. We've contemplated timescales from seconds to billions of years, distances from meters to light years, and temperatures from thousands of degrees to just above absolute zero. We've seen how the Kuiper Belt connects to broader questions about planetary science, comparative planetology, cosmic history, and our place in the universe. Throughout this journey, one theme has recurred: the tension between wonder and danger, between the scientifically fascinating and the existentially challenging. The Kuiper Belt embodies this tension perfectly. It's a scientifically invaluable archive of solar system history, a source of beautiful comets that have inspired humanity for millennia, and a testament to the incredible progress we've made in space exploration. But it's also a vast reservoir of potential impactors, a reminder of our cosmic insignificance, and a manifestation of the universe's indifference to human concerns. How we respond to this tension says something important about who we are as individuals and as a species. We can focus exclusively on the threats and become paralyzed by fear, or we can ignore the dangers and remain unprepared. Neither extreme serves us well. The mature response is to acknowledge both aspects, to appreciate the wonder while respecting the danger, to pursue knowledge while maintaining humility, to explore actively while preparing defensively. This balanced perspective is, I believe, essential not just for understanding the Kuiper Belt, but for navigating life in the 21st century. We face numerous challenges that require us to hold multiple truths simultaneously. Climate change is both solvable and urgently threatening. Technology offers both tremendous benefits and serious risks. We're more connected globally than ever before, yet face deep divisions. Scientific progress provides unprecedented capabilities, yet raises profound ethical questions. Learning to appreciate the Kuiper Belt's terrifying beauty is, in a sense, practice for dealing with these other complex realities. The Kuiper Belt also offers a kind of existential comfort, paradoxically, through its very indifference. Yes, it reminds us that we're cosmically insignificant, that the universe operates on scales vastly larger than human concerns, and that catastrophic impacts are possible. But it also shows us that we're part of something larger than ourselves, a solar system with a 4.6 billion-year history embedded in a galaxy containing hundreds of billions of stars, itself one of hundreds of billions of galaxies in the observable universe. There's something profoundly moving about connecting to this vast cosmic context, even if, especially if, it dwarfs our individual existence. Moreover, the fact that we can understand the Kuiper Belt at all is remarkable. We're collections of atoms assembled through biological processes on a small, rocky planet, yet we can comprehend phenomena occurring billions of miles away and billions of years ago. We can send spacecraft to visit distant worlds and retrieve data about their compositions and histories. We can look at other solar systems and compare them to our own. We're physically small but intellectually vast, capable of grasping truths that extend far beyond our immediate sensory experience. This capability comes with responsibility. We're likely the only beings in our solar system, and possibly in our galaxy or even our universe, capable of understanding and appreciating the Kuiper Belt's significance. If we don't explore it, study it, and preserve knowledge about it, who will? If we don't take steps to protect Earth from potential impacts, what safeguards exist? We're on our own. There's no cosmic cavalry coming to rescue us from astronomical threats or to explore the universe on our behalf. If these things are to be done, we must do them ourselves. This realization can feel burdensome, but it can also be liberating. We're not passive observers of cosmic history, but active participants. Our choices matter, not to the universe as a whole, which will continue regardless of what we do, but to us and to the future of our species and our planet. By studying the Kuiper Belt, by supporting space exploration, by working to detect and potentially deflect hazardous objects, by cultivating scientific literacy and cosmic perspective, we're taking responsibility for our future in a universe that offers no guarantees. And so we return to where we began. The Kuiper Belt is more terrifying than you think, but perhaps not in the ways you initially imagined. Yes, it contains potential impactors that could devastate Earth. Yes, it reminds us of our cosmic insignificance and the universe's indifference. But the deepest terror might be existential rather than physical. The realization that we're alone in our responsibility, that no external authority will save us, that we must be our own protectors and our own meaning makers in an ancient and indifferent cosmos. Yet alongside that terror is beauty, the beauty of ancient ice preserving memories of creation, of comets that have inspired poets and prophets for millennia, of human achievements in exploring realms once thought forever beyond our reach, of mathematical elegance that allows us to predict and understand phenomena billions of miles away. The Kuiper Belt is terrifying and beautiful, not despite these contradictions, but because of them. It challenges us to be brave enough to seek knowledge even when that knowledge is uncomfortable, to appreciate wonder even while acknowledging danger, to remain curious even in the face of vast uncertainties. This is the gift the Kuiper Belt offers, not comfort or certainty, but perspective and purpose. It shows us where we came from, hints at where we might be going, and reminds us that we're part of a cosmos far grander and more ancient than our brief individual lives. Whether we find that terrifying or beautiful, or, as I hope I've convinced you both, depends on how we choose to engage with these truths. The exploration continues. New missions are being planned. Better telescopes are being built. The next generation of scientists is learning the tools they'll need to uncover the Kuiper Belt's remaining secrets. And somewhere out there, 4 billion miles away, countless icy worlds continue their silent orbits, preserving their ancient stories, occasionally sending emissaries sunward, waiting patiently for us to visit and learn what they have to teach. If this deep dive into the terrifying realities fascinated you, check out the video on the screen, where we examine why humanity's dream of becoming an interplanetary species might be far more nightmarish than the optimistic visions suggest.